So let's look at Iota Propane. This is the example that's in your book. And anytime I'm dealing with NMR, I like to draw out all the hydrogens. It makes it easy. And this is actually quite convenient if it's a small molecule. So for 1 iota propane, we'll just draw it out in stick form. And of course, this is what 1 iota propane looks like. This is the number 1 carbon, the number 2 carbon, the number 3 carbon. All the hydrogens are listed. And we have the iodine atom there. Now, if you look in your lab manual, you'll see what the Nmr spectrum looks like. I'm going to try to redraw it here. And we're only going to look in the region of the Nmr spectrum that's relevant for this particular molecule at this point. So on the y-axis, you have the intensity of the signal. And of course, on the x-axis is the parts per million, known as the delta. And for this molecule, we're only going to look from about 0 to 3 parts per million in the Nmr spectrum. And if you look at that spectrum, what you see is around 1. You see what appears to be 3 lines in about this ratio. Okay. We call that a triplet. Anytime you have 3 lines that are in a ratio similar to this, we call that a triplet. Around 2, we have 6 lines. And we're just going to call that a multiplet. And at around 2.9, so pretty close to 3 out here, we have another triplet, something like that. And it's a little smaller than the triplet that we see at 1. We also notice that there are some numbers underneath our ppm that are listed. I'm going to write those above the signal just for clarity here. 3 to 2 to 2. These numbers are the integral numbers. So here we have a signal at about 1, we have a signal at about 2, and we have a signal at about 2.9. We have 3 signals. That seems to make sense. And we have the integration that says 2 to 2 to 3. If we look up here, we can easily identify which signal is which based on the integration. So if we look at this triplet, we notice that we have 3 protons. The only carbon that has 3 protons is this methyl group. Here we have 2 and here we have 2. So now we have to make a decision as to which one is the correct one. Well, it turns out that if you have an electron withdrawing group, something like iodine, for example, the signal is going to be shifted what we call downfield, or closer to 10. Okay, so we have downfield going to the left, upfield going to the right. And so this one that integrates to 2 should be this one. And then this one that has 6 peaks, that has an integral of 2, should be this central carbon. So I'm just going to label these alpha, beta, and gamma. Erase that, make that a little better for you. Gamma. Alpha, beta, and gamma. Alpha, alpha, beta, and gamma. So now we know where our signals are. That doesn't tell us much about what's going on with the splitting, though. And you'll recall that I told you that the splitting was due to n+1, but I didn't really tell you what that meant. So this is known as the n+1 rule for protons in proton NMR spectra. N means the number of neighboring protons plus 1. So your splitting will be equal to the number of neighboring protons plus 1. If we look at gamma, gamma has 3 protons, but they're all the same, and they give rise to this one signal. But beta is its neighbor, and there are 2 protons. So 2 plus 1 is 3, and that's why we get a triplet. If we look at beta, okay, beta is 2 protons. Those are the same type of protons, so they give rise to this signal. However, there are 3 neighbors from gamma and 2 neighbors from alpha. That's a total of 5 neighboring protons, which should give rise to 6 peaks, and that's what we see. Now for alpha, Alpha has 2 protons that give rise to this signal. That's why we have the signal with the integration of 2. However, these 2 protons have 2 neighbors. And so those 2 neighbors, quote unquote, split the alpha protons into a triplet. Okay, and so that's why we have a triplet for 3 for the methyl, because of the beta protons that are splitting it. That's why we have 6 lines for the betas, even though it integrates to 2, because there are 5 neighbors. And we have another triplet for the alpha protons because it only has the 2 neighbors from beta. Okay? Now it turns out that things will shift further downfield if they're electron withdrawing. So any type of electron withdrawing group like a iodine will shift that signal down further. And since alpha is directly connected to the electron withdrawing group, it appears the furthest downfield. Beta is closer to the iodine than is gamma, and that's why beta still appears a little further downfield than gamma. So the closer you are to an electron withdrawing group, the further downfield you're going to be. The further away you are from an electron withdrawing group, the more upfield you're going to be. Okay, so we have downfield, upfield, splitting patterns, integrations. We got a lot of information on this very simple molecule from this Nmr spectrum. And basically what this spectrum is, this is the MRI image, if you want to think of it that way, for this molecule. Just like when you go to the doctor and you get an MRI, they get an image of what you look like based on NMR. This is that image of what iota propane looks like based on Nmr spectroscopy. Now that seems like an awful lot of information, and it is, but it's very, very useful, and we can interpret the spectrum quite easily given some practice. And I can't emphasize that enough. This is not something that you can become good at immediately. Practice, practice, practice has to take place here to get good. But fortunately for us, one of the easy things to do is if you start off with an Nmr spectrum, usually we go from about 0 to anywhere from 12 to 10 on the delta, on the ppm. Okay? And really all you have to do is look at the spectrum and find 5 and draw an imaginary line. And that breaks it up into regions, just like we broke up the IR spectrum into several regions. We can break the Nmr spectrum up into several regions as well. If you're upfield of 5, so between 5 and 0, this is going to be the SP and SP3 region. So any hydrogens that are attached to either SP or SP3 hybridized carbons, they're going to appear over here, okay, as a general rule. And if you're downfield from 5, so from 5 to 10 to 12, this is known as the SP2 region. Okay? And so simply by inspecting an Nmr spectrum, you can tell whether or not you have SP and SP3 hybridized carbons with hydrogens attached to them, or SP2 hybridized carbons with them. Now, close to 0, somewhere between 1 and 0, 1.5 to 0, somewhere in that ballpark, you're going to have things that are just simple aliphatic carbons with hydrogens attached to them. Somewhere around 2.5 or so, you're going to have SP hybridized carbon-hydrogen bonds. And further down from that, so somewhere between 3 to 5, you're going to have hydrogens that are directly attached to a carbon that's very electronegative. And I'm just going to represent the electronegative group as X. So if X is fluorine, it's going to appear further down than if it's chlorine. If this is a nitro group, for example, it's going to appear quite far down. And so we can kind of gauge what we have based on that. Now downfield of 5, close between 5 and 6, you're going to find things like alkenes, hydrogens that are attached to an sp2 hybridized carbon of a typical alkene. A little further down, between 7 and 8 usually, you're going to find hydrogens that are attached to a benzene ring. So that's going to be somewhere between 7 and 8. And further out around 10 to 12, you're going to find things like aldehydes. Okay, that's attached to an sp2 hybridized carbon, so that fits, but it's going to come pretty far down, somewhere around 9 to 10. And between 10 and 12, you'll find things like carboxylic acids. The hydrogen for carboxylic acid will appear way down in this region. Even though that is not attached directly to an sp2 hybridized carbon, we still place it in the sp2 region. That's where it appears, and the group itself is actually attached to an sp2 hybridized carbon, so it appears quite far down the field. Okay? Now, this is a quick way to determine whether, what types of hydrogen you have. If you see signals in this region, you know you've got something like this. If you see something over in here, you're probably going to have an aldehyde or maybe a carboxylic acid. And if you have things in this region, you know that that's kind of the aromatic region. So immediately you can kind of get an idea of what types of groups are present in your molecule just by simple inspection, drawing a line at 5. And then you can fine-tune this by looking at the tables in your lab manual or your textbook to really pinpoint what type of group it is. And you're going to be practicing that in lab. So now I want to do an example that's not in your book. And what we're going to do is we're going to predict what that NMR spectrum should look like for the molecule.